When you picture our solar system, what do you see? You probably imagine the sun at the center, with the planets gracefully orbiting around it. But there's a remarkable and often overlooked feature to this celestial dance. All the planets, from fiery Mercury out to distant Neptune, travel on almost the same flat plane. It's not a random, chaotic swarm of worlds moving in all directions. Instead, they trace out paths on a vast, invisible disk, like marbles rolling in concentric grooves on a perfectly flat tabletop. This shared orbital plane, known as the ecliptic, is a profound clue about our origins, a relic of the violent and beautiful processes that shaped our cosmic home some 4.5 billion years ago. This ordered arrangement is one of the most fundamental characteristics of our solar system. If you were to look at it from the side, it would appear incredibly thin. The orbits aren't just similar, they are almost perfectly aligned. It's a beautiful, elegant structure, a cosmic ballet performed on an immense flat stage. Why should this be? Why aren't the planets scattered in orbits at all angles, like bees buzzing around a hive? The answer lies not in chance, but in the fundamental laws of physics that govern the universe, laws that transform a shapeless cloud of gas and dust into a system of worlds with such precision and grace. The question of this flatness takes us back to the very beginning, to a time before the sun was a star, and before the planets were anything more than scattered grains of dust. It forces us to consider the raw materials from which everything we know was built. Imagine a vast, cold, and dark cloud of hydrogen, helium, and tiny specks of rock and ice drifting through the interstellar medium. This was the nebula that would one day become our home. The story of how that enormous, featureless cloud transformed into the beautifully ordered, flat system we see today is one of the great triumphs of modern astronomy, a story of gravity, spin, and cosmic inevitability. Understanding this structure isn't just about satisfying our curiosity, it's about piecing together our own history. The alignment of the planets is a fossil record written in the language of motion. It tells us that all the planets were born from the same rotating structure at the same time. They are siblings, formed from the same spinning disk of material that once encircled our infant sun. By studying this flatness, we can rewind time and witness the birth of worlds. We can see how the universe, through its immutable laws, creates order from chaos, building intricate and stable systems like our own across the vastness of space. To understand why a spinning cloud flattens, we need to think about a concept from physics called angular momentum. It might sound complex, but you've experienced it yourself. Think of an ice skater spinning on the spot. When she pulls her arms in, she spins faster. When she extends them out, she slows down. What she's doing is conserving her angular momentum. It's a fundamental law of nature. In a closed system, the total amount of spin or angular momentum must remain constant. It can't just disappear, it can be transferred or redistributed, but the total amount is always conserved. This principle is the unseen hand that sculpted our solar system. Our story begins with that gigantic, slowly rotating cloud of gas and dust I mentioned. Every particle within it had some tiny random motion. But when you add up all those random movements across a cloud that is light years wide, you inevitably get a slight overall rotation, a gentle, collective spin. As gravity began to pull this immense cloud inwards, something remarkable happened. Just like the ice skater pulling her arms in, the cloud began to spin faster and faster as it contracted. The conservation of angular momentum demanded it. Now imagine you're a tiny dust particle inside this collapsing, spinning cloud. Gravity is pulling you towards the center from all directions. However, the spin creates an outward force, often called the centrifugal force. This force is strongest at the equator of the spinning cloud and weakest at the poles. So, while gravity can easily pull material in from the top and bottom, the spinning motion resists this collapse along the equatorial plane. It's a cosmic battle between the inward pull of gravity and the outward push of rotation. The outcome of this battle is what defines the shape of our solar system. The material along the axis of rotation, the top and bottom, has little to stop it from falling inwards, so it collapses down. But the material in the plane of rotation is held up by its own momentum. The result is that the cloud flattens. The once spherical cloud of gas and dust inevitably pancakes into a thin, rotating disk, a bit like a potter shaping a lump of clay on a spinning wheel. This structure, known as a protoplanetary disk, is the birthplace of planets. a direct legacy of its birth. This story, from a spinning cloud to a flat disk to an ordered system of planets, is a beautiful theory, but science demands evidence. We can't travel back in time to watch our own solar system form. So, how can we be sure this is what happened? The answer is that we can look out into the cosmos and see other solar systems being born right now. With powerful modern telescopes like the Atacama Large Millimeter Submillimeter Array in Chile, we are no longer guessing. We can actually see these protoplanetary discs around distant young stars. These observations are breathtaking. We can see young stars surrounded by vast, flattened disks of gas and dust, just as the theory predicts. One of the most famous images is that of the star HL Tauri, located about 450 light-years away. The ALMA image reveals a stunningly detailed disk with dark concentric gaps within it. These gaps are almost certainly being carved out by newborn planets as they sweep up material in their orbits. It's a snapshot of a solar system in the making, and it looks exactly like the model we've built for our own origins. It is, in effect, a baby picture of our solar system. What's more, when we discover planets orbiting other stars, exoplanets, we find that many of these distant systems also appear to be flat. The Kepler Space Telescope, for instance, discovered thousands of exoplanets by watching for the tiny dip in a star's light as a planet passes in front of it. This method, known as the transit method, works best when the planetary system is aligned edge-on to us. The fact that Kepler found so many multi-planet systems means that their orbits must be aligned on a single plane. If planets orbited their stars at random angles, it would be exceptionally rare to see more than one of them transit. So the next time you look up at the night sky, remember that the ordered, flat nature of our solar system is not a unique coincidence. It is the signature of a universal process, governed by the elegant and unwavering laws of physics. From the spin of an ice skater to the grand architecture of the cosmos, the conservation of angular momentum shapes the universe. The flatness of our planetary home is a profound connection to the countless other worlds forming across the galaxy, a beautiful reminder that we are part of a vast cosmic story of creation.